For my first talk, I talked about introduction to the whole system. The second talk, I pretty much emphasized the uRiKA appliance. And in this talk, I'll be talking entirely about the XMT, nothing related to the uRiKA appliance. Because as of now, there are different ways of approaching and working with the XMT, either programming it directly in C++ or working with it through the uRiKA appliance framework. So both are worthwhile, and we hope in future versions of the uRiKA appliance to provide an API so that you can both program in C++ and access the data structures inside uRiKA. Okay, so first I'll talk about what multithreading is good for, a little more about the XMT architecture, talk about programming, though in a different way than John talked about it. This is a bit more of a high-level view rather than examples. Talk about some of the performance tools we have. Okay. Why did we go ahead and invent such a machine? As John mentioned, there's three different approaches that have been used in the past to work to get around the speed wall between memory latency and processor clock. Vector processors with amortizing over a very large number of fetches, cache-based, bring in small sets to reduce memory latency, and finally, the multi-threaded processors tolerate memory latency. I think is the most sensible approach. The two most important things necessary to support parallelism, it's probably to support multi-threading, is for your problem, when you're looking at an algorithm to see if it's a good match for the XMT, you want to be sure that parallelism is abundant and that data locality is scarce. And the reason for those two things, parallelism is extremely important for the multi-threading model to work because you need sufficient parallelism in your algorithm to hide the memory latency. The hiding of the memory latency, the multi-threading trick works very well so long as you have at least some reasonable level of parallelism. Serial codes run extremely slowly on the machine, I'm afraid. And data locality is a bit more subtle because the XMT works very well on problems where data locality is abundant. The problem is there's probably a cheaper and faster machine that can do it. So if you're working on a dense matrix problem or something that, like LinPack, that has very good data locality that can be exploited, the XMT will do it very well, but some other machine with a higher clock speed will do it faster. The XMT clock speed is 500 megahertz, and a Xeon or whatever thing might be 3 gigahertz. So, however, the special multi-threaded model works very, very well where caches do not, or vectors do not. And so basically, there's a certain subset of application space that a multi-threaded machine has all to itself. And that's one that's defined by these two ideas. So when you're thinking about a problem and what machine to put it on, think of abundant parallelism and scarce data locality. And of course, two examples we've been talking about all day. Semantic databases, where you're jumping around all over the database, anywhere in the database at any time. And then big data, where data locality is scarce. If it's easily partitioned and there's a lot of locality, then a Hadoop cluster might work better for you. But if indeed you are, the way that you are accessing your data leads you to all corners of the data set, then multi-threading will work the best. Yeah? Oh, absolutely, yes. When we often say it's not the best platform for floating point operations. It's not because it does poorly at them. It certainly has full IEEE floating point. It's just that when you think of a big teraflop machine like an XE series or something like that, those are usually machines that are assuming a lot of data locality where caches work. So for big scientific codes, we don't recommend the XMT, but it takes a long time to explain that. But there's nothing wrong with the XMT's floating point performance, except that it runs at 500 megahertz. We can guarantee very high processor utilization, and you can use all the same memory tricks that we've been talking about on floating point numbers as well as integer numbers. But the thing is that for a lot of floating point work, a lot of floating point scientific work that one sees, there are faster processors. Yeah. Yeah, so it's a messaging problem that we have. We say this isn't a great floating point machine for most scientific work, but the real reason is because most scientific work, people have figured out clever ways of using caches. Oh, that's a good example. Yeah. Actually, I'll put that on the next version of the slide. That's a very good point. Not that many machines will actually support as large a parallel shared memory bank as this machine will, and not in as scalable a fashion. So I'll put when you need to. Well, that's implied in these two. Okay. You can see that this is the same diagram that John put up earlier, but just try to explain it in a little more detail. Basically, you have the register set and program counter for each conventional processor, feeds the arithmetic logic unit. For the multi-threaded processor, all of those register sets are duplicated many times, and each one of them is selected. It makes a complete context switch every clock tick. So every single clock tick, it goes to another one of these hardware streams, as they're called, and starts doing the work from there. I had a question during one of the breaks that was, and this diagram, unfortunately, can be confusing because it looks like it's working like a Gatling gun and spinning around and selecting these things in order. And if it were, in fact, selecting them only in order, there are various memory access patterns that would have a problem. But in fact, it is jumping about rather than doing these in any sort of order. There is a pool called the ready pool and a pool called the wait pool. And so the the processor is continually selecting things from the ready pool and feeding them to the ALU and operating the instructions. And being in the ready pool means that all of its remote memory accesses have been satisfied. So it has everything it needs in all of its registers to execute. And then it will execute, and it will keep on being placed back in the ready pool until it has a remote memory reference, and then it's placed in the wait pool. And it will sit in the wait pool and hang out in the wait pool until the memory request comes back from the memory subsystem, and then it's moved forward to the ready pool. So this is it's a very dynamic algorithm, and that's basically the secret of the whole multi-threading process. But I'm afraid that we haven't figured out a beautiful PowerPoint simulation of showing that would show this, I don't know, 2 sets of these hardware streams moving back and forth. And so this diagram is a little bit deficient. But the important thing to think about is that there's a ready pool and a wait pool. And the streams are constantly being moved back and forth between them. Yeah. As far as I know, it takes an arbitrary thread in the waiting pool. John, do you have any idea? Oh, question of when the next in order? So it's round robin out of the. Yeah. It doesn't make much of a difference, but I didn't know what the algorithm was. Okay. Yeah, and since their position in the ready pool is somewhat arbitrary, you could think of it as random selection, but I guess it's not. So okay, so that's the multi-threading made simple. And the purpose of this really is, as I've mentioned to a couple of people, is keeping all of the bottlenecks in the machine saturated. With a conventional processor, when you've got requests in flight to memory, requests in flight to the network, the processor, when it is not able to fulfill a request because it's not in cache, or even worse if it's a thing, it will actually stall and stop issuing memory requests over this bus or over this bus. So when the processor stalls out, these resources are going wasted. The multi-threaded processor basically uses that multi-threading trick to keep on, when one thread stalls, it will keep on firing requests to the local memory subsystem and to the network. So you could think of memory bandwidth and network bandwidth as being the most precious resources in the machine. And I know that you're all HPC people, and you've heard the old joke about a supercomputer is a device for converting a compute-bound problem into an I/O-bound problem. And the corresponding joke that we always make is a multi-threaded processor is a device for converting a latency-bound problem into a bandwidth-bound problem. So when you're programming the machine, the most important thing to think about is not in your head. You don't want to think about memory layout since you can't control it. You don't want to think about order of operations or anything. The most important thing to think about is memory bandwidth and conserving this memory bandwidth. And that's bandwidth both to its local memory, but really it's sending read requests out over the network. So that's why in the canal output, they always tell you how many read operations and the ratio. You can quickly see the ratio of read operations to floating point operations and other operations. It gives you counters for both. So it's not always possible to control that in all of your algorithms. I mean, many of them have their own built-in number of reads that are necessary for every operation. but you want to make sure that you're not making unnecessary memory access requests. So you're really trying to conserve network bandwidth on the machine. And this is the reason why we hash the memory addresses all over the machine, is to load balance that as easily as possible. So the ideas behind programming this processor are a little different than you're used to. You know, there's no worry about load balancing of computations, or no worry about data locality or data placement. But you do have to think about basically conserving overall memory bandwidth across the machine. And that's usually the first thing that will run out when you're running a really large problem. Okay. We've already covered most of these, but basically one thread will not delay the others. Memory and network bandwidth are the most valuable resources. The main, at least from a uRiKA concept, the main reason we like this model is because it enables the construction of this very large global shared memory bank that we need for the database. But this is also true of graph problems too. Actually, John's lectures showed very well why you need this very fine-grained synchronization. Because when you have so much, the parallelism is very necessary for the operation of the multi-threaded processor. But with that much parallelism, you really need cheap synchronization. That's one of the problems with OpenMP on a small number of processors, is the synchronization is relatively heavyweight. And so when you're talking about thousands of processors instead of just 4 or 8, cheaper synchronization is necessary. So you can certainly think of it in terms of just global shared memory and abundant parallelism. Okay. In terms of the architecture of the machine itself, some of these things have been mentioned. We still have the protection domains. Data locality is not critical. I think that we've mentioned all of these things. One point is that the bisection bandwidth scales with the number of processors as any 3D torus, as with our other machines based on a 3D torus. An interesting thing is this is a completely interrupt-free architecture. So even the operating system is completely interrupt-free. There is not an interrupt structure, which just required a different approach to writing an operating system. All of the hardware threads are allocated on a per-process basis by the runtime attached to your process. So say that works very well for an interrupt-free system. Okay. This is a different way of looking at a diagram I made earlier. Here's a logical view with the two operating systems. So MTK on all of the compute nodes. These are all ThreadStorm processors in Opteron sockets. Service and I/O nodes are all Linux. And when the machine was originally designed, these so-called service and I/O nodes were only primarily used for simply I/O, user login, job submission, and things like that. One thing that's new about the uRiKA appliance is that these are being seriously used as part of the main program. So the uRiKA model is truly hybrid. Before these, I mean, before in the big XE systems and things, you don't tend to do any calculation on the service nodes. Usually, the user isn't even allowed to use them, as far as I know. But in the uRiKA model, you're putting significant computation on the login PEs. We're also adding more compute nodes, such that you can load up the service nodes with serial work and work that is written in languages other than C++. Most of the database world is based on Java. So you have to have some place that we can run Java in the system. So that goes on to the service nodes. And of course, all I/O is connected off of these service nodes to Lustre and to the outside network. Any questions on that? This may be familiar to people who work at a Cray shop. It's our standard model. And then there's a pretty picture of XMT, but we actually saw one in person just a little while ago, so that's not a surprise. It even looks like it's about the same size. And then this shows a compute blade, which I guess we didn't get to see today. You can see the 8 Opteron or ThreadStorm sockets and RAM, and then the C-star chips connecting to the outside network. Yeah. There's what? It's actually a single ASIC. The ThreadStorm processor contains the memory controller. And, okay, I know why you asked the question. Yes. Yeah, ThreadStorm 4. The piece of silicon itself always contains the memory controller and the ThreadStorm processor. If you have a memory-only blade, there are ASICs that are listed as memory controllers that go into those same sockets. And those are actually versions of the ThreadStorm processor with the CPU disabled. So they are used as memory controller-only chips, but it's the same processor. I mean, it's the same piece of silicon. It's sort of like on some multi-cores, they'll disable some, they'll disable cores that are bad, or if you need more dual cores, they'll disable 2 of the cores. But the socket, I mean, this is an Opteron socket, and of course any Opteron always contains a CPU plus a memory controller. And in order to fit the ThreadStorm into that same socket, we had to put the memory controller on chip. Let me see. It's in this case, it's dual channel DDR2. I think it's the same specification as an Opteron. I believe that that Opteron series supports dual channel. Yeah. So truly, to the outside world, it does look like an Opteron. It just submits different things. Actually, at the end of the slide set, I have a diagram of a blade with the memory controller chips in there. Perhaps that'll make it a little clearer. But did that answer your question? Okay. Okay. Yeah, I've mentioned this to a couple people. I wanted to get to this slide because this shows the basic XMT programming model. And really, the best way to think about it is as a single processor with, even though you have, you think of it as a 64P machine, or you might have submitted a job on 8 processors or something like that, you have to actually throw away that idea that you're running on 8 processors. The way to think of your job, no matter how many processors it's attached to or anything like that, is as a single processor with the number of threads that you've attached to it. If you double the number of processors you ask for, you simply double the number of hardware streams that are available. But it's really acting as just one processor connecting to a very large shared memory bank. And this is actually one of the more difficult ideas to really get in your head. If you've been working, as I have, on distributed memory machines for many, many years before I worked on this thing, even in parallel with it, it's hard to get away from this idea of which work is on which processor and where is the memory. But when you're writing an algorithm, just think of a big pool of threads on this side and a big pool of memory on the other. And it's all connected on a single network. And that is as much as you can ever program to, really. So are there any questions on this particular thing? Yeah. me see. Yeah, they're, I think it's a very long instruction word that's, I think 3 instructions are packed into a single instruction word, if memory serves. And so I believe that's to reduce the load on the. Yes. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Right. Locality in terms of the register sets. Yes, yes, you could. It would depend on your problem. The most important thing is to make sure that you have sufficient parallelism in your application to be able to make multi-threading work. So that might be, it goes algorithm by algorithm, but as long as there are a few hundred threads. So if in coarsening it you made fewer threads, then that would be not be a win. Other than that, I think the compiler would take good advantage of it. It does have, I believe, 3. I've not seen anyone attempt to program it that way. Usually the problem is getting enough fine-grained parallelism. So the general idea with the XMT is to go for finer and finer and lighter weight threads. Yeah, yeah. So it's counterintuitive that you would try to make heavier weight threads. That said, I worked on a neutron transport algorithm for this, where the outer loop was over an inner loop body that was 80 pages of Fortran. So it's possible to have very, very, very heavy loop bodies. And that achieved actually extremely high parallel efficiency on thousands of threads, because in that case, each individual iteration was completely independent. So it can work to have very heavyweight threads, but in general, it's best to think of lightweight threads. Yeah, that would be difficult. So it depends. Yeah. Uh-huh. Mm-hmm. How? Let me see. Scheduler, yeah. You know, I actually do not know what the allocation algorithm is, because in general, you don't. It doesn't have the usual constraints. Yeah. Yes, you can certainly, on your 64 processor machine, you can allocate many 64 processor jobs. I truly don't know. It's since I'm an application programmer, I never think of placement. So I actually have never inquired as to what the placement algorithm is.
Okay, I think here's a very important skill. Is another book is coming from outside, most of the students will probably know the trade. For example, I would like to go to run a Maltby or computer or just to see how the system will be scaled up according to the data set. To play around with the
Yeah. Okay. The operating system people certainly will play with that, but from a programmer's point of view, it's not something that you should always assume that. Basically, just trust the machine for a lot of things. There are very few of the classical controls that you have on the other Cray systems or any other distributed memory systems. Maybe John knows. John, wake up. Do you have any idea what the placement algorithm is for the placement algorithm for placing jobs on the XMT processor? Yeah. 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 Okay. Yeah. No. As I say, I believe that the operating system people can do that for debug, but there is nothing anywhere in the programming environment that lets you allocate processors. Yeah, there is no batch system. Oh. Yeah. Oh, yes, I guess I should have said that. No, I say there are a lot fewer knobs on this machine than on many others, but the runtime does a very good job of allocating and scheduling. In, yeah. Uh, yeah. And in our, there's performance tools that go along with the machine that actually give you a nice graphical display of streams requested and stream utilization and things as your program is running. So you can get feedback. I hadn't thought of the example of, you can also program some of the more exotic counters and save those and things like that. So you can actually get all that information if you wish. It's not usually reflected back to the user, except for in the profiling tools. So. Okay. Oh, was that any more questions on the programming model? That is one of the most important things to realize about the machine. It's a little different than what you're used to. So we have a single compiler for the uRiKA, automatically parallelizing C++ compiler. It's a cross-compilation environment. It runs on the login nodes and creates a ThreadStorm binary. It does a very good job of automatic parallelization. You can turn parallelism and parallelization on or off using compile time flags. And then there are also directives that are used to provide hints if you know more about the problem than the compiler does. So you have quite a bit of control over the parallelization. But usually you try to do as little as you can and let the compiler do the work of parallelizing. Login nodes run standard Linux. Hybrid programming model is possible and encouraged. As I say, that's what we're doing on the uRiKA appliance, is making use of all the processor types that we have. In my previous slide showing an API between the front-end nodes and the back-end nodes, I showed communication across the two operating systems. One way of doing this is using what's called lightweight user communication, or LUC. And it's basically, you can build a client-server style interface between the front end and back end. So you can do part of the processing on the front end, part of the processing on the back end. And it's basically it looks like a remote, looks like an RPC interface back and forth across the interface between the file systems. And LUC does operate on the high-speed network because the service nodes are connected to the high-speed network, and so are the ThreadStorm nodes. But for direct communication between the front end and back end, you typically have to use LUC. It is not automatically parallel. If you wished to do, the Lustre file system is automatically parallel, of course, but LUC is not innately parallel. You can manually use multiple LUC requests. And then, of course, the Lustre global file system is automatically parallel, and it's the same one that we use on all the rest of our machines. So that's basically the tools you have to work with. The XMT compiler was designed and built at the same time as the ThreadStorm chip. So they're very closely coupled. So really the best way of getting any performance out of the machine is to trust the compiler. See, I mentioned the types of, you don't trust the compiler? No, trust the compiler to do a good job of parallelization. And though, of course, trust but verify, I guess. You look in the canal output, see what it actually did, and then you use some pragmas to fix that up. But the fewer pragmas and the weaker the pragmas that you use, the better performance that you will get. So basically, it has incremental recompilation, so it uses a program library that it builds as you build your project. So the basic reason for the program library is to allow the optimizer to do a good job of interprocedural optimization. So, but it also saves your compile times and incremental linking. And then we have a debugger and the Cray suite of performance analysis tools, Apprentice 2. Okay. When you're programming XMT, it's often best to sit back and start with a clean sheet of paper and think about the basics of the algorithm that you're working on. It's actually somewhat difficult to port codes that were originally written for, say, an XE6 or something like that to the XMT, because the parallelism for the XMT that the XMT works best on is very finely grained. And so if you have well, I mean, I guess on a distributed memory machine, it's a serial program on a node. If it's a OpenMP style program, it tends to have relatively heavyweight threads, though some OpenMP programs do work well. But it's nice to step back and think about your algorithm and see what the largest degree of parallelism you can wring out of it, and then think of what the compiler will make of that. And this sort of takes some experience to try to get used to thinking like an XMT compiler. But it's very heavily dependent on the success of the compiler and spotting what's in your algorithm. So keeping, as John was saying earlier, to simple loops, inductive loops. And so what we like to say is that programming performance is a negotiation with the compiler. You try something, you throw it over the wall to the compiler, you look at the canal output, see what it thought of it, how it organized, and then you work back and forth. For a very simple loop, you'll often hit it on the first try, but usually you go back and forth looking at the canal output and at the output of the performance tools. Actually, I think that John already covered the concept of pragmas. And these are, you can change scheduling, might be useful for some algorithms. You can actually create loop futures, which are separate subprograms, as John mentioned earlier. They look like a C function. It'll actually spawn a new one thread will result in an additional number of an additional amount of parallel work. And then there's the simpler ones, assert no depth, and then more powerful assert parallel. So the pragmas we've only covered a really small fraction of the pragmas here, but you do have some levers to try to tell the compiler how best you think this program should be parallelized based on your human knowledge about it. So the compiler's smart, but in theory you're smarter and you know everything there is about your algorithm. Okay. Now, potential architectural bottlenecks. It's really not, typically the processor utilization is high and processor throughput is not the problem. As I say, it's turning a latency-bound problem into a bandwidth-bound problem. Network bandwidth is the most precious resource. For smaller size systems, 128 processor. Usually can support about 180 outstanding memory operations. And finally, for the, when you get up to a larger and larger system, the bandwidth starts to trail off a little bit. So minimize the number of loads and stores if possible within your algorithm. This also shows why in the XMT2 we've supported the concept of memory-only blades, where we are not actually using the additional processors and simply use them as memory controllers such that you can get to the really large memory. People often buy the machine for really the large shared memory pool. Okay. This one I think I've mentioned before, but sequential code is truly awful because it's still hashing the memory accesses across the entire machine, but it is cache-free. So you really have to watch out for sequential code anywhere. So when you're selecting an algorithm, think of Amdahl's law. If it has significant serial bottlenecks in it, then there's nothing you can do about it. Think cleverly, but it may not be a candidate for the XMT. I've mentioned that the memory references are hashed. As a result of this hashing, all jobs, no matter what size they are, use all the memory in the system. So if you think about it for a moment, when you're doing a graph computation on 16 processors of a 128 processor system, it's actually significantly faster than 16 processors on a 16 processor system. And that's kind of counterintuitive, but just think of all the additional wires and all the additional memory controllers that you're able to utilize. So because you're spreading this load out over the entire system, basically there's just, and it's hashed, there's simply more bandwidth between you and all of the memory. So it's an interesting wrinkle. I'm not sure you can program against this, except always to allocate as many processors as you can possibly get. But it certainly is a consideration. If you have allocate the most number of processors you can get. Okay. Any other questions on programming the XMT? As I say, that was kind of a high-level view, but mm-hmm. Let me see. Well, if you're lucky, it depends on how the original OpenMP program was structured. The MTA directives are very similar looking to OpenMP directives, and we've had several requests actually for OpenMP for the machine, and it wouldn't be that difficult to do. John, have you ever made OpenMP for this machine?
Yeah.
I don't think it does, yeah. Yeah, basically it should be a very simple conversion, but you may have left a lot of parallelism on the table in those heavyweight threads, because that's you know how you would if you're optimizing for a different weight of thread, then you'll make different decisions. And, Mhm. Yes, actually, that's a good point. If you've got a code that's just coming up to you, you do search for the OpenMP pragmas and say, aha, this is where they're doing all their parallel work, and then see what you can do with it. Oh, thanks. And there's another. Mm-hmm. Yes. Unfortunately, sometimes additional levels of abstraction can interfere with creating loop structures that the compiler can understand. I mean, they've done a lot of work with the standard template library to try to inline functions as much as possible, things like that. But if they're doing a lot of if they're doing mallocing new arrays and working with them and then passing them back, things like that, sometimes that can using a complex structure inside a parallel loop might interfere with its parallelism. So in general, I guess it's really a matter of taste. I'm afraid I tend to write C for the machine mostly, for the lower level loops. But I guess the only answer is it depends. I'm sorry I can't give you a clear. Yeah. Mm-hmm. Well, I do know that there are libraries which have already been optimized for the XMT. Like the MTGL is very boost-like and things like that. And we certainly have worked very hard to make sure that our standard template library is as modern and as performant as possible. So it goes on a function-by-function basis, I guess. Okay. Other questions? Okay. Okay, the performance tools are basically very similar to the ones that you have on the standard Cray systems. Under the Apprentice 2 framework, I have the same GUI application for working with all the different tools underneath that. You can either work with the GUI or generate reports. Canal, John has already showed several good examples of using canal feedback to figure out what the compiler was thinking and how information be utilized. Traceview, or Tview, is actually one of the most useful things when you're debugging your program and trying to figure out its performance. It basically plots against time the hardware counters that you select. Since the processor was designed for HPC, there are actually quite a few performance counters built into it. And you can use Traceview to actually dump those. You compile for Traceview, then you run your program, and it dumps the contents of those different counters to a file. And then you actually run Traceview, and you can see exactly what it's doing. You can zoom in on sections of your application performance, detect hotspots. You can display the number of traps that are occurring. Traceview is really one of the most useful tools for a quick and dirty way of figuring out where your performance problems are. Just basically ask for one that's instrumented for Traceview, run it and watch it, and you can see what's happening. So that's a quick way of finding a problem. If you'd like very detailed information about your performance, you can go to bprof and you can ask for certain counters to be dumped and get profile tables and work with performance information to the third significant figure. So you can actually go as detailed as you want with bprof. Oh, okay. I won't go through this again because we've already seen it. Basically, you can see that it calls out your loops and tells you what it thought about them. Okay. Here's a picture of Traceview running. And this is the execution time of your program. And you can show you can show different, right up here, it's kind of, I'm afraid, hard to see in the corner, but there's different colored traces here. The red trace is utilization, the green trace is availability, and the blue trace is memory concurrency. So you can see that this vertical axis is right now scaled in the number of processors on this side, and over here on the number of memory references. So you see your program start here, and it's hard to read this, I'm sorry. It starts off single processor. It's its first parallel region, and you've asked for 16 processors, so it goes up, and you can see that CPU availability is there's plenty of threads available. Now, unfortunately, you're not getting full utilization. And you look through this red trace here, and you see, oh my gosh, it's getting no utilization, single processor utilization, et cetera. And so you try to figure out what the problem is, and you can see that there's a summary down here that actually shows what happens at different points in the program. You can click on the different sections and find out where it was in the program. You can actually put your own comments. You can put labels in your program, and they will come through and be displayed on this graph. So if you have a particular section that you are worried about, you can label it with a pragma bad section, and then if indeed the bad section shows up there, you can see what. So when you're optimizing, this is probably one of your most used tools. In the apprentice window, you can see you can have multiple tabs open, so you can actually click on an area and then look at the canal report for it. So it's a very quick way of getting back and forth and immediately figuring out what parallel loops and which subsections are doing what. So it's very useful. And then, as I say, for more finely detailed performance profiling, you can open a bprof window too. I'm sorry, another unreadable slide, but it shows the number of streams, shows mallocs, how many functions were called, et cetera, and sums for the entire program, or for sections of the program. And you can work back and forth between Traceview, Canal, and bprof, and so get a very detailed picture of your performance. So just to summarize, the multi-threaded programming model works best for the high degree of data parallelism and a large fraction of remote references. I know I keep saying that, but it's the way that you really select for an algorithm that will really shine on this machine. It goes without saying that the main difference between the XMT2 and the rest of our line is just this custom multi-threaded processor and the custom operating system that it runs on. Thinking in parallel, as much parallelism as possible, and negotiating with the compiler is your best way to get good performance. And then you can get a very, very detailed look at how your program is running using the array of tools. So that's my best philosophy on how to work with the XMT2. Thank you.